Hey, this is Horner, and this is the 2013 question number 3 solution. So here we've got a disc that has a mass of 2 kilograms and a radius of 0.1 meters supported by this rope, and the rope doesn't have enough mass to be any concern, so we can just kind of ignore it. It's attached to the ceiling, and then there is also on this end something pulling it up and applying a force, hence the FA. So first thing they want us to do is calculate the magnitude of the force FA necessary to hold that disc at rest. So let's go ahead and start by drawing a free body diagram for this situation. So we're going to make a bigger dot this time, and it's because we've got a couple spots here where you're going to have the tension in the rope is attached to that disc. So pointing straight down is going to be mg, so that's a typical thing. But then on this side of the dot, you'll want FA, which is that applied force. And on the other side of the dot is FT. So now that we have those, we need to think about what is the sum of the forces equal to. Well, this system is not moving at this point, so it's not accelerating at all. So we know that the sum of the forces here should be equal to 0. We have two forces pointing up, and we have mg pointing down. And so you know from just doing any type of statics problem that these two forces need to be the same. And if they are the same, we're just going to say here that the force of tension is equal to that applied force. Now, if one of them was larger than the other one, then the system would accelerate upwards. But right now they are the same. So we're going to say Ft equals Fa. So we can say that since we have two forces here, the force up is just going to be 2 times Fa. And we are trying to calculate Fa, so that would make sense that we would have to do something like that. Now at this point, since these are both Fa, we have 2 Fa pointing up, so that's 2 Fa, minus, and then pointing down is mg, and that is equal to 0. So now we can just go ahead and solve for Fa. So Fa is equal to add mg to both sides, divide both sides by 2. And now we can plug in our numbers. So Fa is equal to 2 kilograms times 10 meters per second squared divided by 2. The 2's, of course, cross off. So your applied force here is equal to 10 newtons. Points on this one are pretty easy to earn. Really, it's this part right here, where you solve for, you're just showing that the sum of the forces is 0, is worth 1 point, and then the rest of it up through this answer would be the second point that you would end up with. So let's go ahead and take a look at the next part. So at time 0, the force Fa is increased to 12 newtons. So now we have Fa at time 0 is going to be greater than Fa when there wasn't anything going on at all. So we've increased the force. We know the difference in the two is about 2 newtons, and it does accelerate upward. The rope does not slip on the disc, and that's a good thing. Otherwise, we'd have to kind of factor in friction and some things, kinetic friction. And they want us to calculate the linear, so notice the word linear here. They want us to find the linear acceleration of the disc. So this time our sum of the forces is going to be equal to mass times acceleration. So let's think again about that picture that we had. So here we've got our wheel, has a radius r, and I'm actually going to put that radius r on both sides. I know that I have Ft on this side, and over on this side I have Fa. But this time my Fa is a little bit bigger than Ft, so I'm actually going to extend that arrow up so that you can see that. And then straight down we still have mg. So if we do the sum of the forces here, what we're going to do is we're going to say Fa, okay, plus Ft minus mg is equal to mass times acceleration. So that's the first part. The second, and we're going to call this equation 1, so I'm going to put it in a box. The second thing that we need to do is we need to do the sum of the torques, and that is going to be equal to I, the moment of inertia, times alpha, which is the angular acceleration. So we've got two torques going on here. We have one from Fa and one from Ft. And remember, torque is basically just force times that lever arm. Because it's at a 90-degree angle, we don't have to add sine or cosine to it. So we have two torques working about the outside of the disk. And so we know we've got a clockwise and a counterclockwise. FA is going to give us a positive torque, and FT is going to give us a negative torque because this one is rotating clockwise. So clockwise, and we know that that's going to be negative. And then this one is rotating counterclockwise, and so that one's going to be positive. So let's go ahead and plug those in. We have FA times R, and where R is our radius, so let's go ahead and make these capitalized. Minus, now we have this one is, yeah, it's correct, that's FA times R is positive, minus FT times R. So you're really adding the two, but because this one's negative, you get FAR minus FTR. That should be equal to the moment of inertia, which they told you is mr squared over 2. And we multiply that times our angular acceleration. Do remember that angular acceleration is equal to A over R. And so let's get everything in a linear sense here, since we're trying to solve for linear acceleration. So now we can plug everything in. We're going to say FAR minus FTR is equal to mr squared over 2. And we're going to multiply that times alpha, but in a linear sense. So that is A over R. So at this point, we're going to go through and cross some things off. So we can cross off an R that's on the top on each side. And then the other thing we're going to do is cross off an R on this side. Got one on the top left and one on the bottom. So now we are left with the equation FA minus FT is equal to m over 2 times A. And so this is our second equation. So this is equation number 2. Now that I have those two equations, we're going to combine 1 and 2. And we're going to make a new equation. So let's do this one in black. If I add the two equations, I'm going to, so it's this equation and it is this equation that we're adding. So here we go. We're going to have FA plus FA. So that's FA plus FA plus FT minus FT, because I have plus FT and minus FT. And then I have still left on this side is minus MG. And that is equal to, here we've got MA. And we're going to add that to plus MA over 2. Okay, so our issue that we have now is we need to go through and we need to combine these. So we have FA plus FA is going to give me 2 times FA. FT minus FT is going to cross off, so this is minus MG. And then MA plus 1/2 MA is going to give me 3/2 MA. At this point, we need to keep moving. So here we're going to go ahead and solve for A. So I want to solve for A. I'm going to multiply both sides by 2/3. And when I do that, I'm going to have 2/3 of 2 times FA minus MG is equal to M times A. And so at this point, I just need to divide both sides by M. And when I divide both sides by M, I end up with 2 over 3 times, and then I'm going to have 2FA over M minus, now remember when I divide both sides by M here, I've got the M under here, minus, and then these M's will cross off, but I can't cross it off because I still have this. So minus G, and that is equal to A. So now we plug all of our numbers in. 2/3 of 2 times 12 is that new force, and we're going to divide that by 2, which is our mass, minus 10. And you could use 9.810 is absolutely fine then. And that will be equal to A. So in the end, our acceleration here is equal to 1.47 meters per second squared. So not a lot of physics, but a ton of algebra. So just kind of keep track of what you're doing. The physics is where you're going to earn the points. So let's go through, and I'm going to put all the points in green that you would earn on this one. So you would get 1 point for doing sum of the forces. You get 1 point for solving for sum of the torques and getting the sum of the torque equation to become this guy down here. So you also would get a sum of the torques equation point. So there's 3 points right there. And then when you combine the two and get a final answer, that's where that last point comes in. So that's the 4 points that you would end up with in that section. Next thing they want us to do is find the angular speed of the disk at 3 seconds. So this is actually a nice, really easy thing to do. So we know that the angular velocity is equal to the original angular velocity plus alpha times time. And we know that alpha is equal to a over r. And so here we know the original is equal to 0. I want to now plug everything in. So our final is going to be equal to, so this guy goes away. I have alpha. So what do we say alpha was? Alpha is a over r. And we want a because that's what we solve for here. That just makes it easier. And so now we have to also multiply that times t. So it was alpha, which is a over r, times t. That will be 1.47 times the 3 seconds. And we divide that by the radius, which is 0.1. And we end up with 40 radians per second. Points on this one, you get 1 point for having the equation, plugging in alpha so that you have a over r instead of alpha, and then doing the number thing. And that will be your 2 points there. The last thing they want us, well, second to last thing they want us to do is calculate the increase in total mechanical energy. So remember, mechanical energy is going to be the spring energy, gravitational potential energy, kinetic energy, and then we have rotational kinetic energy. So remember that's 1/2 I omega squared. So here we go. Let's go ahead and start by identifying the energies that are there. So we know that our total mechanical energy, so our change in energy here, is equal to the change in the potential energy plus the change in the kinetic energy. So there's no spring energy in this one at all. Let's think about our kinetic energy. So our kinetic energy here is equal to our linear kinetic energy plus our rotational kinetic energy. So our linear kinetic energy is 1/2, and then we have m, and then we have final velocity minus original velocity squared. We don't have an original velocity, so this is just really 1/2 mvf squared, but we're doing this so we see that it is a change in kinetic energy. Plus 1/2, and then that's times I times omega final squared minus omega original squared. So there's our equation for a change in kinetic energy. We also have a change, let's put this over here, change in potential energy due to gravity. There's no rotational part for it, so it's just mg times that drop. Now, one thing we don't have is we don't have the height. But we do know we can do mg, and then remember the equation delta y is equal to VOT plus 1/2 AT squared. We don't have an original velocity, so our delta y can just be then equal to 1/2 AT squared. So that's a substitution that you have to learn to use. Now we can go back and let's change colors since we're adding some things together. So we're going to plug in delta K here, plug in delta UG here, and let's see what we get. So this is equal to mg times 1/2 of AT squared plus 1/2 of mv final squared plus 1/2 of I omega final squared. And I didn't include the finals, it just becomes redundant after a while. Now that we have that, we need to go through and let's change some things here. So we do have a linear acceleration, but we have a rotational, we have something that's rotational. So we want the rotational piece in here. So remember we said that the rotational speed is 40 radians per second. So it's okay to mix them here because everything will work out in the end. So because we're solving for, all these are going to end up with joules. So delta energy here is our mass times gravity times 1/2 at squared. We need this thing to go from rotational to from linear to rotational. So this is going to be 1/2 of mass, and then this is going to be, remember, V is equal to omega times R. So we're going to take omega times R and square it, plus 1/2 of the moment for this disk, mr squared over 2, and then that's times omega squared. So we know omega, we know the linear acceleration, but in the end these all give us joules, so it's okay to have both types of motion in there. So at this point we have 1/2 mg at squared plus, and then all of this, if you want to, you can combine it and it becomes 3/4 mr squared omega squared. If you don't want to combine it, you can just plug the numbers in. So it's totally up to you. Delta E then is equal to 1/2. Mass is 2, gravity is 10. We said the acceleration is 1.47. 3 squared is our time, plus 3/4 of 2 times 0.1 squared times our omega, which is 40 squared, and that's equal to 144 joules. So where do we get points for all this stuff? First point is conservation of energy. That's typically a point. Next point that you're going to end up with is when you do the kinetic energy, it's really just making sure that you understand that these originals are 0. So you get 1 for recognizing what the kinetic energy is. Then you get 1 for plugging these two things in together for the total energy. So they want to see the physics, essentially, is what it is. From there, it's all algebra, and so you only get 1 point for that part. For letter E, they do actually give you a point for checking less than, so that's 1 point. They don't always give that point. Now, if you would check greater than or the same as, or check 2 things, then they won't even look at your reasoning because you've missed it. So the rotational inertia, so they want to know the disk is replaced by a hoop. The hoop rotational inertia is greater. So the rotational inertia for a hoop is much bigger than it is for a solid sphere. I mean a solid disk. So here we're just going to say the rotational inertia of the hoop is greater than that of the solid disk. Remember, because all that mass is on the outside. And we have to make sure 2 things. We have to make sure that the radius and the mass are the same. And so here, a solid disk of same mass and radius. And because of that, therefore, the acceleration of the hoop is less. And why is that? Remember, we know that the torque didn't change, but our I went up, so our alpha has to go down. This went up, so alpha has to go down, and this remains constant, or it is the same. Where do you get points for this bottom part? You end up with getting a point right here, and then you have to have a valid explanation. And so that would be this. If you just said the rotational inertia of the hoop is greater than the solid disk of the same mass and radius, you don't get the point. You have to go back and relate it. You have to use the therefore. The acceleration of the hoop is less based on this equation. So that's it. And those are the 15 points you get for this question.